are going to perform all the necessary operations to set up the analysis for SeaKeeping. In this case, it will be a response amplitude operator analysis. So first of all, you have to configure the analysis, which we can do either through this start data window, which you can see now in your screen. There we go. In this case, the analysis is already chosen. As you can see, it's going to be a waves environment analysis, and the type of analysis is SeaKeeping. You can see here you have these options in the selected problem side of the window. So we hit OK in this window, and that will configure the data tree for the desired type of problem. Okay, now, so we can see the data tree. We can either click this icon at the left upper corner of the interface, or we can bring along the data tree by the menu options. You can see here, data. Okay. So here we have the data tree for configuring the analysis. If you click this red part of the window, it would be inserted in the interface, as you can see, the left part of the interface. And now, well, all the data, the configuration data of the analysis which have been performed through the start data window can also be checked here in the data tree. So of course the problem can be defined from the data tree. I have here in the problem description you see here problem setup, the environment, and the type of analysis, which are already chosen, but this could also have been done from here instead of the start data window. So now let's get into the main problem. The first thing we have to define in this case is the bathymetry of the problem. As I said before, we had defined a domain of 120 meters depth, and we will make it coincide with the depth of the problem. So choose constant depth, and that would allow us to insert the depth, which of course is 120 meters. We are going to define this beach or absorption zone for about 70 meters. So the waves are well absorbed before reaching the edge of the domain. And now we can continue to the environmental data. In this case, can define the waves spectrum, which for the response amplitude operator analysis is going to be white noise. As here down in the lower part of the interface, we choose the white noise spectrum type. we are going to choose a range of analysis which goes from 8-second to 28-second period. So here in the shorted period field we'll get the 8, and in the longest period field we'll set it to 28. We are going to analyze with 20 waves periods, and of course the amplitude is going to be 1. So we click OK. And we head on to the next definition of the problem. We're going to set the time data. We're going to set, in this case, the simulation time to 600 seconds. Time step 0.3 seconds. And the start time, recording time, would be 300 seconds. And we will set an initialization time of 200 seconds. Well, regarding this simulation time and time step, in this case, in this type of analysis of response amplitude operators, these two parameters of the analysis, simulation time and time step, will be automatically changed and set by the code once the analysis has begun. So we can see that later. And we can continue to define the body data, the floating body data, in this case the semi-submersible structure. And we're going to define some different data, which would be, for example, the center of gravity, the radius of duration, the degrees of freedom, the mass, and in this case also we are going to define external forces, which will be representing two springs located at each one of the legs, and this is just to avoid the structure to go along too much in the search direction. And well, when defining these external forces, that also obliges us to define a moment, a restoring moment, to annulate the moment created by the forces, the spring forces we are defining. So the mass, in this case, is going to be defined as a function, and will be the self-displacement of the submerged volume, and it can be defined using the internal variables of the code, in this case the volume and the density. So the volume times the density would be the displacement, and that's going to be the mass of our floater. The next thing to do is to define the center of gravity. In this case is going to be center in the origin, the center of the object, but the set coordinate is 0.85 meters. The next step is defining the radius of gyration. In this case, we can define the matrix, well, defined as a matrix for all the different movement directions. In this case, just diagonal of the matrix defined with the same radius of gyration. We have, let's see, 31.06 for X, Y, and Z axis. The same for the three of them, 31.6, 31.06. Okay, so we hit OK, and the radius of gyration have been already defined. And to make this window bigger, so you can see the tabs in the upper part for the different body definition options. The next step will be to define the degrees of freedom we want to analyze. In this case, we want to define the search, HIF, and pitch degrees of freedom. Okay, and now, as I was mentioning before, we're going to define external forces in the x-axis, and the point of application would be each of the legs. So it's like we are defining two springs, one in each leg, to avoid the structure to go along the x-axis, and we can define it via a function. So we will create a function for the external x force, and we just insert it manually. The total force is 1.0 E5, but these forces are situated, as I said, in each of the leg. So we will have to define the coordinates of application, and particularly the displacement of those points of application. So the force will act as a restoring force, as a spring. So let's define it. 0.5 e to the power of 5 times the displacement you see there. Dx is the internal variable code for the displacement of a certain point. The point which I'm going to define now would correspond to a lower point in the lower part of each of the legs. So minus 40.28 7.36. You see I'm defining the coordinates of this point, x, y, and z. Minus 17.55. Okay, and now I have to define the remaining force applied to the other leg, which will be the same. So I'm going to copy the function and just paste it. So the only difference of this other component would be that the y coordinate of the point where it is applied is minus 27.36, because it corresponds to the y coordinate of the other leg. So we have to find this load. I'm going to copy it all for reuse it for defining the moment, and hit OK. And we are going to define now the external moment in the y-axis, the same methodology, creating a function. First, I'm going to paste the formula I have just copied from the x-force I created. So now we just have to add to each term of the formula, we have to add the z coordinate of the center of gravity. So we can create a moment. You can see here. This would be the height of the application point refer to the center of gravity, so we can annulate the moment created by the external force we have applied, 16.7, and we do the same for the other term of the formula. We add this height. So right now, as you can see, we have a moment. It's a force times a height, so it's a moment. And well, that would be all. Okay, so we have the external forces defined. In this case, you can see that there are some more tabs like initial position or initial velocity. These tools could be used for another analysis, let's say extinction test or something else. But in this case, we don't have to do anything else. So the only remaining thing is to select the body, so apply these properties to the floating body. And for doing so, I'm going to open again the layer window and switch off the rest of the layers and just leave the floating body layer on, so I can easily apply the condition on the surfaces. You can do a render so you can see it better. Okay, so just click select and select actually the surfaces, and that would be it. So a group, as you can see here, called body data auto 1 is created. You could choose another name, of course. I'm going to create it, to call it semi-sub body, semi-sub body. You can see here, change the name and just click OK here, and we're done with the body data definition. I'm going to activate the rest of the layers now, so we can continue applying boundary conditions. Close again the layers window, and we go to the section of the boundary conditions. You can see in the data tree displayed. This case is easy. Yes, first of all, we're going to apply the free surface condition. Just need to select the free surfaces of the geometry. You can see the top one situated in the coordinate 0 of the z-axis. There. Again, we can name the group as we like. Automatically, the program names it free surface auto 1. I'm going to change it just as free surface. Okay, so hit OK. And we got the condition applied. The other condition which we are going to apply is the outlet. So define the outlet of the domain, and select, and just select the outlet. You can see there in red, and just change the name to outlet, for example, and hit OK. So now we can see the groups created for the different conditions. You can see here a group called free surface and another group called outlet. And now if we wished, we could draw them, so we can see we have assigned them to the correct surfaces. You can see here, hit draw, right click on the groups with both of them selected, draw groups, And there you can see from the bottom side in yellow the outlet and in green the free surface. Of course, we can do the same with the body data group. In this case, we just have one floating body, but of course the program allows to define several bodies, so we can do multi-body analysis, also with links between them. But in this case, just a single body. We draw it just the same. Right-click on the group, draw, and draw groups option. So there you can see pink color, the part of the geometry assigned with the condition body, which is obviously what we wanted. So in this case, you see that also there's a bottom condition, but this should be used only when the depth of the analysis is much larger than the actual height of the geometry, of the domain geometry. So in this case, it coincides the depth and the height of the domain, so no need to define the bottom boundary condition. So yes, we have left just to go through the numerical data, but in this case we can leave everything as it is. Yes, by default is already set to the solver and preconditioner, which is indicated for this analysis. What we could do is to choose, for example, to use, let's say, 2 processors if the computer actually has more than 1 processor. And there are some options here. For example, if your computer includes a graphic processor unit, GPU, you could accelerate your analysis choosing a combined CPU and GPU calculation, which is not the case. So we could leave it as it is, and of course we could save the model. This is a advisable thing to do in general. And we'll call it, for example, webinar example, which is very original. Okay, so now our unnamed model has a name. It's not an orphan right now.